Hey there, my name is Alejandro, and welcome back to day 96 of me doing the NeetCode 150 challenge. So today we're doing another LeetCode Medium 1D dynamic programming problem, and without further ado, let's get straight into it. Okay, today we get a LeetCode Medium problem 647, Palindromic Substrings. It seems like we've solved this before. Given a string S, return the number of palindromic substrings in it. A string is a palindrome when it reads the same backward as forward. A substring is a contiguous sequence of characters within the string. Okay, so first things first, this is a problem that we covered inside of our lectures at the University of Toronto Scarborough for our advanced algorithms course. And the way that my professor taught me how to solve this problem was with 2D dynamic programming. I'm going to guess that this problem is essentially almost exactly the same as the last problem. It's just that instead of trying to find the longest palindromic substring, you're essentially going to every single time you encounter a substring, you're going to increment your counter by 1, right? So we'll solve it in two ways. The 2D DP way, which I'm going to guess is okay, yeah, because we have up to 1,000 characters, and S consists of lowercase English letters. So if anything, they might go as the exact same cases, right? So I'm just going to do this in a similar style as the last problem, where I'm going to do 2D DP first, because I think that's intuitive, right? These are substrings, so it's a very intuitive way to do 2D dynamic programming, where you have an index I and an index j, and essentially you return true or false whether the string is a palindrome or not, right? So here I'm going to write a def DP. It's going to take itself, it's going to take an index I and an index j, right? And here we'll have, a self.memo. This DP of I, j returns true if and only if S from I to j is a palindrome. Otherwise, returns false. There we go. So here we'll have this, and for I in range a length of S, for j in range, from index I all the way up to a length of S, we're going to do index I, not I plus 1, because, every single length 1 string is indeed a palindrome. And here we'll just say count, or here we'll just say result is equal to 0. And here we'll do res plus or equal to self.dp of I, j. And then we'll just return res, right? And so something like this will work. And so here I can just say, if I is greater or equal to, so here we'll say, if I, j in self.memo, then return self.memo of I, j as always, right? Otherwise, we'll just do the cases where it's odd length palindrome. If I greater or equal to j, then return that I is equal to j. If if I is equal to j, return true. Even length palindrome. If I plus 1 is equal to j, then return, here we'll say self.s, self.memo is equal to s, this. Return self.s at index I is equal to self.s at index j, right? And then we'll say if I is greater than j, then return false. Then it will do if self.s of I doesn't equal self. So here, if anything, it's one even length palindrome. Here, this case 2, a length palindrome. If I is greater or equal to j, return I is equal to j. And here we'll do self.s of I doesn't equal self.s of j, and return false, cannot be a palindrome. Otherwise, we'll be okay, from I to j, if I doesn't equal j, then it cannot be a palindrome, right? Because the point is that, you essentially have a center, like in the last video, and you expand and so on, right? So, for example, a palindrome like race car, right? The point is that, this r must, that's the last character, must match this r that's the very first character, right? And then you can essentially get rid of them, right? And that's for the rest of this, check if it's a palindrome and so on, and keep going, essentially, work your way through 2 pointers all the way up to the center, right? Where the center is either 1 character or no characters, right? Or 1 character or, 2 characters, right? So it's this in this case, it's when you get rid rid of these A's, and then you get rid of the C's, you're left with one E at the end, right? But you could imagine if you had a palindrome like beep, right, and you get rid of the B's here, right, you don't have a single character as your center, you have two characters, right? So that's why it's like I do, like, you know, if you're down to two characters, then just return whether or not they're equal. Otherwise, it's like, you know, you'll get to a case where it's like an odd-length palindrome, and so if I is greater or equal to j, return I is equal to j, right? So at that point, it's like if I is equal to j, return true. Otherwise, like, you know, if I is greater than j, then return false, right? Because it's like you surpassed, right? So there we go, bada bing, bada boom. Otherwise, we'll say, let me think here. Yeah, here we'll just do res is equal to self.dp of I plus 1, j minus 1, because now we've checked the indices at index I and j. Then we'll say self.memo of I comma j is equal to res and return the res, right? Make sure that you cache, and there we go. Something like this should be nice and handy dandy and work just perfectly, right? There we go, and we can submit this. If it's fast enough, and there we go, bada bing, bada boom, we have a working solution. So now this is obviously like, you know, 2D dynamic programming, right? So I'll call this DP2D. I'll call this so anywhere that I have DP in an open parenthesis, I'll call this DP2D with an open parenthesis, right? And there we go. So this was essentially the way that we did it, right? Now 2D dynamic programming solution, right? Now the way that we can do it is essentially kind of the spirit of the last problem. We can come up with a 1D dynamic programming solution, right? So here's like 1D dynamic programming solution, right? And here we'll essentially say, we'll essentially split the problem into essentially figuring out, like, you know, an index I to be the center of every single dynamic programming solution, right? But now the only difference between this and the previous problem is that before we essentially kept expanding until we got the longest possible palindrome starting from a center index I. Here we're still going to find all the palindromes centered at the index I, but just every time we have a new palindrome, we're going to say, hey, this is a new palindrome, and increment the number of counts of palindromes that we have, right? So res will equal to 0 at the very beginning, right? Number of palindromic substrings, right? And then here we'll say for center, here we'll say n is equal to length of s for center index in range n minus 1. Here we need n, right? Because before it was just like, you know, longest palindrome, we don't need to check the last one, but here we might need to, right? Here we'll say case 1, odd length palindrome. So in this case, what we'll do is L comma R is equal to center index comma center index, right? And here we'll say res plus or equal to 1, and then we'll say while L is greater or equal to 1, and R is less than n minus 1, and S of L minus 1 is equal to S of R plus 1. Then we'll say L minus or equal to 1, R plus or equal to 1, and res plus or equal to 1, right? So that's the nice. So we just found one more palindrome, essentially. Then there we go. Otherwise, case 2, it's even length palindrome, right? So here we'll say L comma R is equal to center index and center index plus 1, right? If S of L doesn't equal S of R in the first place, then we'll just continue, right? Otherwise, we'll say res plus or equal to 1, and while L greater or equal to 1, and R less than n minus 1, and S of L minus 1 is equal to S of R plus 1, then we'll say L minus or equal to 1, R plus or equal to 1, res plus or equal to 1, and there we go, there we have it. So here we'll just return res at the very end, right? And we can see if something like this works. Does not work. Oh yeah, so we need to say if R less than n and this, right? We're just gonna make sure that. Before we didn't need to just because it was this, and here we're missing. So here, are we overcounting by 1? Is that the problem? Seems like we are overcounting by 1. Which one could we possibly be overcounting? Ah, this one over here, right? This might need to be an OR, right? If R is equal to n. Ooh, but do we continue at the very end? Then we might have an undercount, no? Do we not? If r is equal to n, or did we already account it for here as the thing? Did we already account it for here? Right, yeah, so we have the, they have the last single index. We'll have the length 1 palindromic string counted here, right? And so here we don't want to count it at the very end when we don't have a partner for it. Yeah, makes sense. That absolutely makes sense. So yeah, we can run this one more time. And here we can submit it. And okay, it seems like we have at least a much faster solution. We're right on par with the standard deviation curve over here. I don't know if I can make this, too much faster. I'm trying to think. Right, here we can maybe do this. And res plus 1 to account for length 1 palindrome at A1 that was not accounted for in the above for loop. Right, there we go. So maybe we can do something like this. Right, and this should work if we do res plus 1. And yeah, so yeah, maybe we can like make that O of 1 stuff go away. Yeah, okay. My butt that it made that slower. Why the heck would it be slower now? Yeah, okay. But it seems like, we're right on that standard deviation line. So there we go. Bada bing, bada boom. We have a nice and reasonably efficient solution, right? Some people seem to be faster. Maybe that's when there was less test cases, or maybe there's a much faster way to solve this. But I'm just like, okay, this problem is very, 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 very. It's basically the same problem as longest palindromic substring. It's just that instead of focusing on finding the longest palindromic substring, it's just every palindromic substring that you found in this problem that you essentially consider to be the largest, you essentially, instead of considering it to be the largest this time, just count the number of palindromic substrings that you find along the way. So they're very, very, very similar problems in nature, and we can check off the fact that we did this problem right over here. So nevertheless, as always in all my videos, I do a quick recap if I was able to solve the problem. So this one, it was reasonably nice, short, and succinct, just because it was an almost exact replica of the solution to this problem, longest palindromic substring, right? If you've seen that video, then essentially you know that I did this in two ways. One of them is with 2D dynamic programming, right? So essentially, I have a 1D dynamic programming solution as well, and so on, just in the spirit of this being a 1D dynamic programming section. But the very first way that I think is the more intuitive way is essentially we want longest palindromic substrings, right? So here dp of 2D takes in two indices I and j, where I must be less than or equal to j, and essentially returns true if s of I to j inclusive is a palindromic substring. Otherwise returns false, right? And the way that we do this is okay, obviously cache the results and so on. But then we have some base cases, right? So if I plus 1 is equal to j, then that means you have a length 2 string, right? So you have index I and j, which is equal to I plus 1. So you have index I and I plus 1, right? So it's about, if you have a length 2 string, it's a palindrome if and only if those two characters are equal, right? So if self.s of I is equal to self.s of j, right? Now, otherwise, if I is greater or equal to j, there's really two cases, right? If I is equal to j, that means you have a 1 character string, right? So you want to return true if I is equal to j. Otherwise, you want to return false if I is greater than j, right? Because it means you overshot it and so on and something went wrong, right? So if I is greater or equal to j, only return true if I is equal to j, right? Because that means it's like a 1 character string, and a 1 character string is always a palindrome, right? Otherwise, it's okay, essentially the way that we check palindromic substring is you always look at the first and last characters, and if they're equal, then great, you can essentially keep going as a 2-pointer solution, right? So here what we do is okay, if self.s at index I doesn't equal self.s at index j, then that means that this cannot be a palindrome, right? If I have something like race car, which is a palindrome, right? But I make this character a b here, then all of a sudden race cab is not the same thing as base car, right? It must be that the first and last characters are the same for a substring to for a string to be a palindrome, right? So if the first and last characters are not the same, then we return false, right? Otherwise, if they are the same, then we can essentially ignore it for the rest of the problem, right? I can get rid of this r and I can get rid of this r, and then all I care about is whether the rest of the string is a palindrome, right? Because if this is a palindrome and then I have 2 r's on the end, then the whole thing is still a palindrome, right? So what do I want to check? Essentially, if this used to be index I, if this used to be index I and this is used to be index j over here, and now I've confirmed that these two characters are the same, then I only care about what's the inside here, right? So essentially I shift my I over by 1, and my j, which used to be here, I shift it down by 1, right? So here I'll check, self.dp of 2d, which again returns to me true or false whether the substring from I to j is a palindrome or not. Here I'm like, okay, since r and r are equal here, right? So since the original I and j are equal, then I only want to care is this substring palindrome as well, right? So here I'll check like, self.dp of 2d from I plus 1 and j minus 1, where I used to be here, so this is I plus 1, where this I is now, and if this used to be j, then this is now j minus 1, where the j is now, right? So we want to check if this inner substring is a palindrome, right? We'll just catch that result and return the result, right? Which will either be a true or false. And this is nice because again, it's like you recursively call upon the same function over and over and over, which actually makes this a dynamic programming problem, right? Or at least a classical type of dynamic programming problem, and the way that I actually like to think about dynamic programming, right? Now, obviously, this is a 2D dynamic programming solution, and we're under a 1D dynamic programming category, right? And so I did most of the thinking in the last problem, which is why I was able to solve this one so quickly. But essentially, the idea is that, so since you're dealing with substrings, right, the person that really taught me dynamic programming is Eric Dermain, professor at MIT, who kindly uploaded some of his MIT courseware videos online on YouTube for everyone in the world to see. And I really loved his dynamic programming lectures, and he's the one that made dynamic programming click for me. And he always explains that, like, if you can't fit in prefixes, so essentially a prefix means like, do dp of I, where it's like, you solve the result from like, s of I onwards, if you want to do suffixes, or otherwise like, s from 0 up to I inclusive and so on. The problem is that like, it's very tough to like, find like, number of palindromic substrings up to index I and use that result to find the number of palindromic substrings up to I plus 1 and so on. That is very, very weird, right? Because here you're dealing with substrings. And he says like, when you're dealing with prefixes and you end up needing suffixes, or you play with suffixes and you end up needing prefixes, usually that means you don't want to go the prefixes or suffixes route. You want to go the substrings route, right? Which is why it's so intuitive in this problem. Like, we're literally dealing with substrings to do a 2D dynamic programming problem where we deal with substrings, right? And by the way, this is a piece of advice that I really, really wish I knew when I did my final exam for the Advanced Algorithms course at the University of Toronto, Scarborough, because I got absolutely destroyed. I kept trying to fit the problem into a 1D dynamic programming problem when it was just a 2D DP problem, and there's just like pretty much no way around it unless you really, really did like O(n) work inside the body, which I was trying to avoid. And yeah, so never try to make prefixes or suffixes work when it's pretty much a substrings problem. And I had to pay that price the hard way during my final exam at the University of Toronto and so on, and ended up getting me a lower grade and a lot of stress because there was an auto fail on that problem and so on. So never do that, right? And this problem is a little bit different, right? So obviously prefixes and suffixes is not what we want to deal with, but there is another way that we can approach this problem, right? Each palindrome in the world that you can think of essentially has a center, right? Whether the center is 1 character or 2 characters long, essentially everything on the outside of it is like, like 2 characters that are the same, plus 2 characters that are the same, plus 2 characters that are the same, 2 characters that are the same, 2 characters that are the same, over and over and over, right? So essentially what we can consider is every single index inside of the length of the string as the center of our palindrome, right? And then for each of those, essentially make that the center of our palindrome and essentially count the number of palindromes that are around it, right? So if you have a single character like A, it's like, okay, are these 2 characters the same? If so, that's another palindrome. Now, are these 2 characters the same? If so, that's another palindrome. And then keep on going and going, right? Now, there's 2 possible cases. You could have an odd length palindrome, or you can have an even length palindrome. If you have an odd length palindrome, right? For example, an odd length palindrome would be something like ABA, right? Where it's an odd length string, but it's a palindrome, right? Essentially, the center is a single character, right? So here I'll say my L and R at the beginning are both the center index, right? In this case, it would be like, this B. And what I'll say is like, okay, a 1 length string is always a palindrome. So I'm going to augment the number of palindromes I have by 1 immediately because I know the length 1 palindrome is valid. And then I'm going to say like, okay, well, L is greater or equal to 1. So essentially here, I want to subtract L and add 1 to R. Subtract 1 from L and add 1 to R if and only if, like, if I subtract L, so essentially it's like, if my L and R are both of this B, ideally I want to make my L point to this A and this R point to this A over here because that would get me to the next palindrome, right? But I can only do so if those are equal. So the very first things I have to make is check that they're in balance, right? The subtracting 1 from L still keep me in balance, right? So is L greater or equal to 1, right? Because if L is 0 and I try to subtract 1, then it doesn't make sense to try to index -1, right? The same thing for R. If I want to add 1 to it, well, then R plus 1 better be less than N, right? So which is the same thing as checking whether r is less than n minus 1, right? And then obviously if they're both in bounds, if I subtract and add to them respectively, I want to make sure that like, okay, if I subtracted l, right, l minus 1, is that equal to whether if I added r plus 1, make sure that those indices, their characters are the same, right? So if s of l minus 1 is equal to s of r plus 1, and those are in bounds, then that means it's like I can expand the palindrome to by subtracting 1 from l and adding 1 to r and finding a new palindrome, right? And that's exactly what I do. L minus or equal to 1, r plus or equal to 1, and then the number of palindromes I see plus or equal to 1 because I just found a new palindrome, right? And then essentially I'm going to take my center index and keep expanding like this and so on as long as I can, and it's the same character, and to count the number of odd length palindromes that are centered at this index, center index, right? Now this is for odd length palindrome. For even length palindromes, I'm like, okay, it has to have 2 characters, so I'll just do center index and center index plus 1. And here I go only all the way up to the second to last character, because I know for the last character the only possible case is for there to be one length, one palindrome, and that's it, which is why at the very end I just do res plus 1 at the very end to account for the very last length 1 palindrome. But otherwise, that's why I don't have to worry about this being out of bounds, right? And then the very first thing I check is like, okay, I want a length 2 base, right, or center, right? Now, if the 2 characters there are not equal, then straight up there's no palindromes from this point on, right? So here I just continue the for loop, right? Otherwise, if they're equal, then first of all, those 2 characters that are the same form a palindrome, so res plus or equal to 1. Otherwise, we're going to just keep expanding the same logic of try to keep expanding 2 characters at a time as long as they're equal from the center base. And as we do so, you know, l minus or equal to 1, r plus or equal to 1, and the number of palindromes that we've seen plus or equal to 1, right? So that point is essentially, it's like for every single index inside of my string S, I'm going to consider that as my center of a palindrome, right? And I'm going to count the number of odd length palindromes that have this exact index as its center, as well as the number of even length palindromes that have this exact center index as its center, where, well, center of index is the left base and center of index plus 1 is the right base because it's a length 2 center, right? And then expanding from that point onwards over and over, right? So for every single index in S, I'm going to essentially consider that index as the center of a palindrome and essentially see how many palindromes expand beyond from that center, right? And then at the very end, I just count the number of palindromes, and at the very end, I just return the number of palindromes, right? So this is how you essentially solve this as 1D dynamic programming, where the 1D dynamic programming really comes from the fact that like you have n subproblems, right? So it's like dp of I, where I is the center of like a palindrome, and like and then you essentially count the number of palindromes from it, and then it's like for every single index I, you compute like, you know, the number of palindromes with that index I as its center, and then take the sum for all of those index I's, right? And that's pretty much the idea in terms of how to solve this as a 1D dynamic programming problem. As we can see, it's like we're right in the middle of the pack with the standard deviation curve, so that feels very nice and handy dandy. In my honest opinion, I think a more beautiful way to solve this is this 2D dynamic programming way, where you just think of palindromes as substrings, and essentially you can essentially relate subproblems to another, where like, you know, dp of ij is connected with dp of I plus 1 and j minus 1, right? Obviously it's like, you know, check if the 2 characters are the same, and then otherwise, like, you know, if they are the same, that means you can expand forward from this, and so that way it's like, you know, you rely on caching and so on, and it's like you don't you essentially do O of 1 work inside of here, and you have O of n squared subproblems, so you do O of n squared total work. Inside of here it's the same thing, right? It's just that I have O of n subproblems, and in each of one I do O of n worst case total work, right? But n subproblems with O of n work each is O of n squared. O of n subproblems with O of 1 work each is O of n squared. So these are both O of n squared solutions. It's just that this is a 2D dynamic programming solution. This is more of a 1D dynamic programming solution, right? And since we're in a 1D dynamic programming section, I wanted to make sure that, hey, at least I solve this in the 1D dynamic programming type of way as one of my solutions. But in my opinion, I much prefer the 2D dynamic programming approach, just because it's like it's much more natural when you're dealing with a substrings problem, the palindromic substrings problem being absolutely no exception. But I guess you're curious of how I would solve this in 1D dynamic programming. This is exactly how, and this is exactly in the same spirit as the very previous problem. If anything, I think this problem may be a little bit harder than this one, because instead of just like, you know, blindly counting every single palindrome that you find, here you're actually interested in finding, like, you know, the longest one. So, but at the end of the day, they're pretty much, you know, cookie cutter, the same exact problem. It's just that one of them you count the number of palindromes, and one of them you just care about the longest one that you end up finding, right? But you have to end up looking through every single palindrome anyway, right? So that's why I say like this one might be easier, because you have to look through every single palindrome anyway, so it's maybe easier to count than just pick the one that's the longest one. But at the very end of the day, it's pretty much the same problem, just that tiny minute little difference in logic. And yeah, but otherwise, hopefully that solution makes sense. And yeah, but otherwise, that's pretty much it for this video. If you did find it useful or enjoyable in any way, shape, or form, I would highly appreciate if you left a like or a comment. But otherwise, I'll catch you in the next one. So till then, ciao, my friend. Bye bye.